So the good thing about the cloudy day by the beach is that we own the whole beach. So,
Right.
and at any rate, we're glad there's no rain, and we look forward to the talk by Hiroshi, who's going to tell us about symmetry in quantum field theory and gravity.
Thank you. Oh, so now its microphone is on. Good.
Yeah.
Okay, so can you hear me?
Very well.
Excellent. So, so I have to be careful not to be too close to the microphone. So the title of my talk is Symmetry in Quantum Field Theory and Gravity, and I will talk about mostly my work to appear in collaboration with Daniel Harrow. So, well, first, I'd like to thank to the organizer for organizing this and giving me this opportunity to talk. And I have given this beach seminar several times, and it's always very enjoyable and relaxing. So I hope that will be the case this time. So during this workshop, there has been a variety of different conditions on low energy effective theory discussed. Those conditions that are sort of expected for theories that come from mathematically consistent ultraviolet complete quantum theory of gravity. And there has been a variety of conditions that have been proposed with argument of various level of rigor. And some are conjecture, and some have a stronger argument for it. And so today I'd like to discuss a set of conditions that some class of conditions that I hope you can give mathematical proof. But of course, as such, it's rather restrictive and so necessarily weaker than some of the other conditions. And so some of the conditions that have been discussed, I think, in this workshop include weak gravity conjecture. And there are a variety of versions of weak gravity conjectures. And so today I will talk about conditions that there are no global symmetry in low energy effective theory of consistent quantum theory of gravity, which in some sense is implied by weak gravity conjecture. So I understand last week my Caltech colleague Cliff Chen gave a proof of weak gravity conjecture. So if you are happy with his proof, then there is nothing I should talk about today. But if you are not satisfied with that, then maybe there is a room for improvement. There is also Swampland distance conjecture that I proposed with Kamran 11 years ago, and there are some relation of this Swampland distance conjecture to weak gravity conjecture that have been discussed during this workshop and also possibly tomorrow. There is also a condition that we have recently proposed about the potential in low energy effective theories. However, there are actually some differences between these type of conjectures. So that I would like to sort of first point that out. So there are conditions that, so suppose somebody give you low energy effective theory. So low energy effective theory comes with some cutoff scale. So we say that we can use this low energy effective theory to discuss physics whose energy scales is less than this cutoff. So if that happens, so somebody give you these conditions, so can you, how much you can actually test whether this low energy theory satisfies these conditions, and then for example, exclude some of the low energy effective theory. Okay, so we might think that well, depending on the version of the weak gravity conjecture, or no global symmetry conjecture, this is something that maybe you may not always be able to test. Whereas these may be something that you can actually test. So let me try to sort of first distinguish that. So for example, so there is a version of weak gravity. There is a weak version of weak gravity conjecture, and there are stronger version of weak gravity conjecture. So the original version says that there is at least one particle of some mass and charge with respect to Maxwell field, so that the charge to mass ratio is bounded. But that conjecture does not say that how big the mass should be. So it could be that if you look at some low energy effective theory with rather low cutoff, then that low energy theory may not contain such a particle in it. So in which case, it may look like that low energy theory breaks the weak gravity conjecture. However, it should be that as you raise the cutoff scale, eventually you should be able to see such particle before you reach the Planck scale. I think that was the sort of spirit of original conjecture. Am I phrasing it correctly?
I think the stronger weak version of the weak gravity conjecture is that the mass is less than m pi.
So that's right. So weaker version of the weak gravity conjecture says that mass should be less than Planck scale. So that means that for given effective theory, you may not be able to test whether it satisfies that condition or not. There are stronger versions of this where you have like a tower of particle, in which case there is a possibility that you may be able to test it. But so not every swampland condition can actually immediately exclude given low energy effective theory. We should be careful about it. And since no global symmetry condition that I'm going to talk about also is sort of closely related to weak gravity conjecture. So as such, it may not immediately exclude given low energy effective theory. So for example, the standard model of particle physics has baryon and lepton number conservation. And it's sort of inevitable if you actually assume the low energy particle content of 17 particles in standard model of particle physics, then it's inevitable that whatever the renormalizable terms that you can write, they all satisfy the baryon and lepton number conservation. So those are called accidental symmetry. So accidental symmetries are not excluded under these conditions. But we would, so what this claim, this claim to say is that before you reach to the Planck scale, necessarily the term has to be generated, which breaks the global symmetry. So for example, in the case of baryon number, for example, most of the grand unified theorem generate dimension 5 or 6 terms that would break a baryon number and mediate proton decay. But this theorem, this claim, this condition does not tell us how and when such term arises. If there is actually a possibility of coming up with some argument that the term has to be, say, power suppressed by some power in Planck scale rather than exponentially suppressed, and we can try to construct such an argument. But it doesn't tell you exactly in which power such term can arise. There could be some further accidental symmetry in high energy which suppresses, say, dimension 5 operator, and then it might appear in dimension 6 operator. So in that sense, these are the conditions that cannot be necessarily tested in a given low energy effective theory. These are the conditions that can potentially be tested within a low energy effective theory. So for example, swampland distance conjecture says that if your low energy theory contains scalar field whose range is parametrically larger than the Planck scale, that should not be derivable from consistent ultraviolet complete quantum theory gravity. So that seems to be something that you can actually test within a given low energy theory. And also the condition for the potential can also be tested in a given low energy theory. So it seems as though there are actually two kinds of swampland conditions. You raise a hand, Simeon.
So,
you can certainly use the microphone to ask questions.
Sorry, I just wanted to ask about the swampland distance. Sorry, the condition, I mean, the condition is that you're not allowed to have long distances for scalar fields.
Right.
But I mean, isn't that Aren't there counterexamples just from like exact supersymmetric moduli spaces and things like moduli can have infinite distance?
You mean that the supergravity theory rather than supersymmetric field theories?
I see. You say this is a flat space.
Well, so for example, n equal 4 super Young mills
Right.
has Planck mass at infinity. So it's certainly not contradicting with the conjecture.
Oh yeah, but I meant something like n equals 8. The compactification of M theory on a T7 or something, right? I mean that has infinite distances.
Well, but if you go travel beyond Planck scale, there will be light degrees of freedom.
I see.
And so that means that your originally effective theory containing given set of particles
I understand.
is violated because you have to include these new light degrees of freedom. So the conjecture is that you give me low energy effective theory, which include all the particle content, and then if the traveling beyond the Planck scale add new particle below the scale, then it's already invalidated there.
I understand. Okay, thank you.
Okay. Okay, so it looks like there are these kind of two different kind of things. And so today I will be discussing this one, which is therefore, for the reason I just said, is inevitably weaker than some of other conditions. But this is something we can actually give a rather strong claim. And so it's good to have a variety of different level of rigor and weakness. So this is what I would like to talk about. So anyway, so the statement is that low energy theory may have accidental symmetry, like the case of a baryon number in standard model. But the claim is that that symmetry cannot be made into exact symmetry in the original quantum theory of gravity. So that would be the claim. Yes, Samson.
We had already discussion last 2 weeks ago or so.
You can use the microphone.
I said that we had already discussed it before. You were not here, but you also will emphasize that this is about internal symmetries. It does not include space-time symmetries like Lorentz group, which is a global group.
So today, for simplicity of presentation, I would like to restrict my attention to a global symmetry which does not mix with space-time symmetry. So in particular, it means that the symmetry operator acts on local operator in the low energy theory, so that it maps that operator to another local operator at the same point. Okay, so this actually so there is some aspect of this specification that requires careful discussion. So for example, there are class of theory for which what seemingly like global symmetry is actually the space-time symmetry. So for example, there can be theory where you have seemingly global symmetry of this type. Say, for example, fermion number parity. So you can say that fermion number parity is a global symmetry that should be violated. But that may not be the case because fermion number parity is the same as a space-time symmetry of 180 degree rotation. So sorry, so 2 pi rotation. So therefore, you cannot distinguish these two symmetry, and so that space-time symmetry may not be broken. So when we talk about global symmetry, it has to be that there has to be some local operator. There have to be at least 2 local operators for which, with the same transformation property under space-time symmetry, which transform differently under the global symmetry in question.
I just wanted to emphasize that many things that we discussed, like mass and momentum and spin, all these are
space-time symmetry.
Space-time symmetries,
yes.
and global symmetries.
So I'm not excluding.
You cannot touch those. They are not broken. They are there. Otherwise, you cannot say what is the mass.
They are remnant of gauge symmetry in the bulk.
Right. So
I'm not going to exclude a non-normalizable gauge symmetry.
So no global symmetry does not apply global symmetry of space-time.
We have already confirmed this for your previous question, that we can make that point. Okay, so But this was a good point to make because what seemingly like global symmetry can be gauge symmetry in disguise. And one possibility is that what seems like global symmetry is actually acting in the same way as some of the space-time symmetry, like 2-pi rotation, for example. So that's one possibility. And another possibility is that in string theory, there are often situations where seeming global symmetry comes from gauge symmetry in higher dimensions. So for example, you can compactify string theory on manifold with isometry, for example. And then that setup seems to have symmetry related to isometry of compactified manifold. But this is really diffeomorphism in higher dimension. And in fact, as a consequence, the symmetry that you get in low energy is not global symmetry, but is gauge symmetry, as Karuta-Klein theory says. But in fact, if you take the manifold, Calabi-Yau manifold or whatever internal manifold, the volume of that manifold to be infinitely large, then you can have decoupled system with global symmetry. But in that limit, the Planck mass goes to infinity because Planck mass is tied to the volume of the internal space. So there is no contradiction of global symmetry be emerging in the limit when the Planck mass goes to infinity.
Without talking about where they come from, how would you distinguish a discrete global symmetry from a discrete gauge symmetry?
So depending on the space-time in which we are discussing things, I will be discussing mostly about untitled space where we can actually prove theorems. And so in that case, there is a way to define what we mean by gauge symmetry, including non-normalizable symmetry at infinity and the global symmetry in ADS. But it requires precise, careful specification of how to normalize gauge symmetry at infinity and how to distinguish normalizable gauge transformation from non-normalizable gauge transformation.
But for discrete symmetries, is there any sort of normalizable versus non-normalizable distinction? You say you still have that distinction for discrete?
So you can ask what the distinction is between the discrete gauge symmetry and discrete global symmetry. Yes, actually, so I would like to spend quite a bit of time discussing the issue of discrete symmetry. So maybe we can defer that towards the later part of the talk. Yes. So he was asking whether we can rule out higher form symmetry, and the answer is yes. But I do not have time to discuss that today. But the answer is yes. Okay. So now let me first review the standard argument for the absence of global symmetry, just to contrast with what I was going to do. So standard argument, which is actually the most easiest to construct, is in the case of continuous non-abelian symmetry, such as SU2. So suppose you say that you have a quantum theory of gravity with Einstein action coupled to some finite number of matter fields with SU2 global symmetry. So then you can have a state with arbitrary spin. And then if you have spin J, the dimension of representation is 2J plus 1. And in principle, you can combine particles with various representation of SU2 to make black hole, which carry global charge of arbitrary J. And suppose I make J to be extremely large. And so suppose you make black hole carrying spin J. And then such black hole, but suppose that we don't add any other gauge charges to the black hole. So geometrically, such black hole will be described, if the mass of the black hole is much bigger than Planck mass, described by Schwarzschild solution. So such solution would decay by Hawking radiation. In the case of gauge charge, the Hawking radiation may discriminate the positive charged particle emitted and the negative charged particle emitted because there is a long-range force between the charged particle and the black hole. However, for global symmetry, there is no long-range force dependent on the global symmetry. That's one of the hallmarks of global symmetry. So therefore, you would expect that Hawking radiation would be neutral under global symmetry charge. So that means that the Hawking radiation would preserve the charge carried by the black hole. So the black hole can shrink. So suppose but then suppose you look at the status of black hole when the mass has been sufficiently released, but still larger than the Planck mass, so that Bekenstein-Hawking formula applies. Then you can have a situation where 2j plus 1 is much bigger than exponential of Bekenstein-Hawking entropy. You can certainly arrange so that j is very large, really large, compared to exponential of Bekenstein-Hawking formula for the mass of a black hole whose mass is bigger than Planck mass. So that can be contradiction because you cannot fit this representation in the number of microstate of black hole. So that's one of the sort of standard argument to try to exclude global symmetry in quantum gravity. Okay?
This assumes that the black hole is already formed. What if I run this argument in terms of transportation?
So Samson is asking, this argument assumes that black hole of charge J has already been formed. So I'm assuming that since you have a variety of particles with various charges under SU2, so by combining particle with, by having a charged particle, a gas of charged particle, and have it collapsed, I'm assuming that a black hole of arbitrarily large charges can be generated. So that's an assumption. Clearly, this proof or argument have various assumptions. This is one of them. And also, you can ask whether Hawking radiation is precisely charge neutral or not. There can be subtle correlation that release charges. So you can actually point out loophole in this argument, which is a very good thing to do because I will give a better argument for it.
One of the things is that I can argue that black hole because of this will never be formed.
Yeah. So you repeated your question. So certainly you can question whether such black hole of large charge can be generated. That's another issue. There are also restrictions on this argument. For example, it's not obvious that this applies to abelian continuous symmetry because all the representations one-dimensional. But here you can have a different representation with different charges. So you might still appeal to the issue with remnant, etc. The argument may be weaker. There is also a possibility, you can also ask whether this type of argument exclude finite group symmetry. So for example, Z2 has only one non-trivial representation, and that's one-dimensional. So it gives plus or minus 1. So certainly, in that case, you cannot construct such an argument. So it appears that this argument cannot exclude finite group global symmetry. So it's desirable to have a more robust argument which apply to both continuous symmetry, abelian or no abelian, and also finite group symmetry or discrete symmetry. So I would like to present such an argument. But I need to actually in order to do that, I need to specify what class of consistent quantum theory of gravity we will be discussing. So I'll be discussing this in the context of ADS-CFT correspondence. So this is restrictive, but at that cost, I will be able to give a more precise derivation of this. So the proof consists of 4 parts. The first part is that, I need to define the kind of symmetry that we will be considering in ADS gravity. So we'll be considering gravitational theory in untitled space, and then we need to define what we mean by such theory has global symmetry. And then, second, I need to specify when it is exact symmetry. So you give me symmetry in low energy effective theory of ADS gravity, and then I need to tell you when we say that this can be regarded as the exact symmetry of ADS gravity. And then third thing is to show that so this is a global symmetry. Show that such global symmetry in ADS is also global symmetry. Global symmetry in the dual CFT. And finally, we want to show that this contradicts existence of such symmetry with gravitational ADS dual leads to contradiction with the locality of physics in untitled space. And here we use entanglement with reconstruction. So, so I do not have time to, so I have already spent like half an hour discussing this. And the music is on, so it's going to be the main part of my talk. And so I will be mostly discuss this part, where I assume that I have shown that if you have exact symmetry in gravitational theory in ADS, then it also implies exact symmetry in conformal field theory. And then I would like to show an argument that leads to contradiction, and therefore excluding such possibility. So I will be focusing on this aspect, although I'd be happy to discuss other steps of this proof.
Any dimension, Hiroshi, or you don't consider 3 dimensions?
So this is so I will be discussing the situation where the bulk physics can be described. So I'm sorry. Question was that whether this argument applies to any dimensions, and so I should specify that I will be discussing class of ADS gravity, which can be described by Einstein gravity coupled to finite number of matter field. So for example, this will not include higher spin theories, which contains infinitely many massless degrees of freedom. It doesn't contain gravitational theory, which deviates significantly from Einstein gravity. And so in particular, gravitational theory in 2 dimensions not included. Gravitational theory in 3 dimensions is a bit subtle because it's not dynamical. But I think that this applies to ADS3 CFT2 as well, provided that ADS3 is described by Einstein gravity coupled to finite number of matter field.
ADS3 case, the problem will be that global symmetry will be infinite dimensional.
So Samson pointed out that in the case of ADS3, the dual CFT may have infinite dimensional symmetry. So I have not told you what class of symmetry that I'll be describing. One of the features of the symmetry should be that it commutes with energy momentum tensor. So Kac-Moody symmetry does not commute with energy momentum tensor. Only the zero mode of Kac-Moody symmetry commutes with energy momentum tensor. So one of the important things that I'm going to use in the proof is that global symmetry must commute with energy momentum tensor, because we would like global symmetry not mixed with space-time symmetry in the strictest possible case. So even in that sense, even in the case of CFT2, the symmetry is actually finite dimensional. Kac-Moody symmetry will not be considered here. Okay? So So I would like to spend the rest of the time, maybe 40 minutes or so that time left with me, discussing how to go from assuming global symmetry that come from ADS gravity, and then that leads to contradiction with locality in ADS. In fact, if in the original case where you have global continuous symmetry with nether current, then we don't have to do much work, because suppose there is a nether current J, then the standard ADS CFT dictionary would tell you that this J will be dual to gauge field in ADS. So as such, the symmetry that is generated by J is not a global symmetry, but is a gauge symmetry. It's done. So it's already contradict with some of these steps when you reach there. So we don't have to do much work when we already know that nether current exists. However, I would like to extend the proof to the case of finite group, for example, where there is no obvious nether current existing. And also, as I point out later, that there are situations where even in the case of continuous symmetry, that there are cases where nether current does not exist, which actually I didn't know before we started doing this work. But such example exists, and it's actually quite natural. And so I would like to discuss some of these possibilities. Fortunately, the people who have been working on algebraic quantum field theory in the past half century or so, they have come up with a better version of nether, well, more general version of nether theorem that apply to all these symmetry, even in the case when you don't have nether current. So under such generalization is sufficient for what we want to prove. So we would be employing it. And so this is based on work by Buchholz, Duplicher, and Lungo, which appeared in Annals of Physics 1989. So this is actually, this sounds a little bit technical, but it turns out that this is actually closely tied to some of the important features of ADS CFT correspondence, entanglement of boundary state and the Ryu-Takayanagi formula, etc. This seems to be closely tied to this kind of concept. So it seems like it actually captures some of the essential part of the ADS CFT correspondence and holography. So I'd like to spend a little bit of time discussing what this means. May I? Thank you. Okay, so when we talk about ADS CFT correspondence and the holographic reconstruction, one of the ideas that often come up is the idea that Hilbert space of boundary conformal field theory can be split into those associated to segment of the boundary region. So split property. Namely, that suppose you have conformal field theory defined on some boundary region, and then you decompose this boundary region into segment, say R1 and R2. Then, when, for example, we discuss Ryu-Takayanagi formula, for example, we say that the Hilbert space decomposed into the one associated to this region 1, and then region 2. And then say that the total Hilbert space is a tensor product of that. So this is often sort of used as a first step in, I'm sorry. I have to rotate this symbol. This is often stated when people talk about the Ryu-Takayanagi formula. This is not precisely true, because if it were true, for example, that we know that entanglement entropy has a universal ultraviolet piece. And if the Hilbert space were to decompose in this way, then there shouldn't be such universal piece. And so this cannot be true. And but there is actually a more rigorous way to formulate what we mean that Hilbert space split. And so this is something that has been clarified by some of the works that preceded this paper. And so I just wanted to first mention that because this is relevant for the rest of my talk. So we say that quantum field theory, so this is not what I'm going to employ, but we say that given quantum field theory has a split property provided that the following is true. So suppose you have a region R in the Cauchy surface of quantum field theory. And suppose I sort of extend it so that the region R contains region R prime. Now, in algebraic quantum field theory, people consider algebra of local operator defined in some given region, which is denoted by A of R. So A of R is, of course, contained by A of R prime. So it's included like that. But split property says that there is actually there is something in between. So split property says that there is a so let me draw this not as a region, but as a space of operators. So there is a space of operator A of R associated to region R. And then there is a space of operator R prime, A of R prime associated to region R prime. And then split property requires that there is actually an algebra in between, which I'm going to denote as N. And then N is what the von Neumann algebra people call as type 1 factor. So type 1 factor is a technical term, but it means that it essentially means that it's a von Neumann algebra whose center is trivial. So that it doesn't have, so the only non-trivial element that commute with everything is an identity. Okay, and the great thing about having type 1 factor, so I should write explicitly because we'll see that later. So N in particular has no non-trivial center. And then one important consequence of this is that it can be represented as something acting on a Hilbert space. So this is almost as good as having this kind of split property, because what it means is that if you have space A, R, and then if you have R prime, which is a little bit bigger than that, and that contains it, and then there is always an algebra in between which can be realized on the Hilbert space. So such an algebra contains all the algebra contains in R, but not necessarily contains everything that in R prime. So in particular, it doesn't contain anything that is outside of R prime. So that means that if you separate the region into region R, and complement of R prime, with possibly some small band in between them, then there is an algebra of operator acting on the Hilbert space, which is called N, the type 1 factor, which contains all the local operator in the region R, and none of the local operator in the complement of R prime. So this is almost as good as this, but not quite. Yes?
In various algebraic descriptions of QFTs, so people talk about short-range versus long-range order and short-range versus long-range entanglement. So does this apply to long-range entangled phases and long-range ordered phases?
So, as far as I know, this property on flat space, Minkowski space, I'm not aware of any counterexample to this case. So that should include the variety of different entanglement property of quantum field theory. And if you have a candidate, so the question, I'm sorry, Sergey was asking that whether this property is about quantum field theory with particular entanglement property. And so I'm not aware of, as I'm going to say, that I'm not aware of any example of quantum field theory where this is false on Rn. So if there is an example that that you can propose, I'd be happy to discuss.
So Chern-Simons, just to make Chern-Simons theory in R3 has no local degree of freedom.
Right. So this has to be augmented to include some extended degrees of freedom. But so for now, let's just discuss the local quantum field theory.
So short range is not
right.
Not including Chern-Simons.
So as R prime approaches R, N just becomes A of R?
No, A of R is not type 1 factor. So that's different. So N is neither A of R or A of R prime. If it were, then the original claim would have been correct.
So what happens as R prime approaches R?
So the question is, what happens to R prime approach? So this statement is not true when R is exactly R prime.
But it can be arbitrarily.
But it can still be arbitrarily close, but not exactly the same.
How exactly are these algebras defined? I mean, they're defined as sort of taking ordinary local operators and integrating them against some kind of functions.
Right. Yeah. So we can go over sort of this lecture on algebraic quantum field theory and discuss how A of R is defined.
But it's not. Yes. It doesn't.
It's a standard definition in algebraic quantum field theory.
Okay, and it doesn't depend on boundary conditions of any kind.
Well, it's a local statement.
But I mean, the definition of these algebras don't require any input about that.
So I think that definition of state requires boundary condition, but not of the local operator, as far as I understand. Okay. So that means that there is some operator which can be realized on Hilbert space. So just to show you that this is actually some non-trivial statement, let me give you a counter example to this. As I said, I'm not aware of any counterexample for quantum field theory in Minkowski space. So the counterexample necessarily has to involve non-trivial topology. So here is a counterexample. So suppose you have a Cauchy surface, which is a circle times a sphere. So suppose we consider quantum field theory in d dimension, So suppose you have d minus 2-dimensional sphere times a circle. So this is a picture where you have S1 in this direction. And then here you have a sphere of d minus 2 dimension. So suppose you have such configuration. And suppose you have just a pure Maxwell theory. So you have a gauge field F. So this is some of the most simple quantum field theories that one can consider. And well, suppose I take the region R to be some band, which is segment in the circle direction and wrapping on the sphere. Now consider a flux of this gauge field on d minus 2-dimensional sphere. Okay? So this certainly, and then if I choose this circle to be in this band, in this region like this, then this clearly is in the algebra of local operator of A over R. Okay? Now, so N is some type 1 factor which contains this. Now, this, however, you can choose A of R prime to be a little bit bigger, so N is included in it. So then clearly, such phi is in the center of N. So first statement is phi is in the center of N. Because I'm considering pure Maxwell theory, so there is no charged particle in it. So the phi has to commute with every local operator. There are no local operators which carries charge. However, at the same time, phi is non-trivial operator. Because even in the pure Maxwell theory, we can consider Wilson line of the gauge field going around this cycle. And it has non-trivial commutation relation with the flux operator. So it has a non-trivial operator in the center of N. So that's counterexample to this condition. So there are certainly quantum field theory on non-trivial topology Cauchy surface, which does not satisfy the split property. And in fact, this has an important consequence to what I would like to discuss, because the thing that was done by this paper by Buchholz, Dupricher, and Longo is that they show that if the quantum field theory has this split property, they show that if the quantum field theory has split property in this sense, then it means that there is actually a generalized version of Noether theorem. So in fact, if you have a quantum field theory like this, so in this particular case, for example, there can be problem with Noether theorem. Thank you. Thank you. There can be a problem with Noether theorem. So let me just briefly discuss that. So here I considered one pure Maxwell theory. But suppose I have sum of two Maxwell theories. Suppose you have a Lagrangian, which is like square. So as you correctly pointed out, I need to dry it.
Normally we distinguish between Noether charges and those who come from the Polish argument, like monopole charges. So we distinguished it to, when we teach, we say that there are Noether charges.
I have not talked about Noether charge yet. I'm going to.
But
this is about split property. This is a counterexample to split property. I have not talked about Noether charge yet.
Well, okay. Maybe I am asked too early. So okay.
But that's not a duality invariant distinction anyway, right?
No, what I wanted to say is that there are many different kind of charges, right? I mean, you can have monopole charge, right? And then you can now start trying to figure out what is the Noether symmetries that this monopole charge comes from, and you will fail. So what we have to do, we have to include all of them in quantum field theory. So, for example, I would say that in regular electrodynamics, there are magnetic and electric charges, and magnetic charge doesn't need to have the Noether current.
So I'm not sure why this is relevant to what I just talked about, because I have not talked about Noether charges yet. So in this case, I'm considering pure Maxwell theory, so there are no local operators which carries neither electric or magnetic charges.
My question was basically about the theorems that you stated about n having no center.
Well, so there is a center. So in this case, there is a center which is non-trivial. That's what I showed. This theory contains a center which is in N, which is non-trivial. So how is that relevant to what you say?
Well, because I would say that all the topological charges that we talk about will be examples which would contradict this theorem.
It was no theorem. So I have not stated theorem. I only stated a definition.
No, you stated theorem about N having no center.
No, it's not a theorem. It's a definition of what we mean by split property.
So, sorry. So if then that's not satisfied, then there is no split property. Okay, thanks.
Okay. Yeah, so I'm not sure whether I answered Samson's question, but not. So anyway, so let's consider the case when we can discuss Noether symmetry, Noether charge. So suppose you have two of these. Suppose you have two pure Maxwell theory. So this theory also have the same kind of problem, because you can have flux for the gauge field F1 and F2, and both of which generate a non-trivial center for this type of algebra. And that means that we don't have split property. And in this case, you have actually U1 symmetry, which mixes F1 and F2. So you can rotate F1 and F2. So you can ask, well, is there a Noether charge, Noether current for this? And you can try to apply standard Noether procedure to construct it. And then the kind of charge that you can come up with is something like A1, AI, which Fj contracted with epsilon symbol. Yes? Yes.
I just wanted to try to understand your example in my language.
Yes.
So if phi crosses the Wilson line, then it picks up like some additive factor, right? Because
right.
Phi. So if this direction is a circle, like if you really imagine a torus,
yes,
then phi does not exist, because once phi crosses the loop, it picks up like a factor of 1, like an additive factor of 1, because it's like the.
So you're saying that it's not well defined.
It's like you try to put the
charge.
charge.
Yeah, but isn't it still operator in A of R prime, which is defined in this region?
It's like asking like what's the electric field on a circle if you have one charge, so it doesn't satisfy the Gauss law.
Right.
So there is no way to.
But there is no charge here.
No,
there's
the Wilson line.
Series.
The Wilson line is a charge.
Yes, the Wilson line is a charge. Yes.
So you like your space is a circle.
Right.
And then you put like a unit probe charge.
Yes.
So how can the electric field be consistent on a circle when there is one charge?
Right.
So what's the answer?
Sorry, so I'm not sure how I understand the question, because I thought that in this pure Maxwell theory, both operator phi and Wilson line operator can be defined.
That's right.
Are you questioning this?
No, that's right. But
okay.
What I'm saying is that when phi crosses the Wilson line, the algebra is that the
what
new
do you mean
phi...
by crossing? Oh, okay.
Crossing.
Okay.
Phi is a topological operator.
Oh, you
it's
mean that you have a Cauchy surface and you put phi first and the Wilson line second?
Yes.
And you do it in reverse direction.
Phi is the generator of a one-form symmetry in 1 + 1. So that's what you're doing. The algebra of phi and the Wilson line is that phi to the left of the Wilson line is, let's say, something.
Yes.
And to the right of the Wilson line is the same plus 1.
Yes, I agree with you.
So now I'm trying to go back. So how does If it's a circle, if your space is a circle, how is it consistent?
What do you mean by consistent? You can.
I'm just saying that putting a single Wilson line in compact space leads to some horrible instability.
So let me try to understand. So you have S1 times SD minus 2. And I first put the Wilson line operator over here and the phi over here. There is a split in time direction.
That's right. We don't draw the time direction.
Yes.
So I'm saying that phi to the left of the Wilson line is the same as phi to the right of the Wilson line plus 1. That's the algebra of these two operators.
When you say left and right, you mean the time direction?
No, in space. The Wilson line is a point in
what
space.
What do you mean by left and right? Because phi, if you consider phi direction and the Wilson line direction, it exhausts all the causes.
Let's take d equals 2. Let's take d equals 2. Okay.
Okay.
Then
d equals 2 means that it just. So this is.
Then this is just a point.
This is just a point, so you just have a circle.
And this is space, not space-time. So
yeah,
circle
it's
is space.
Yeah,
Good.
yeah.
So I'm talking about left and right in space.
What do you mean by left and right? Because Wilson line is wrapping the circle.
He's talking about, I think, the case these three in your line.
S0 is 2 points.
Take S1 times S1 is thinking.
Yeah, I'm talking about S1 times S1. What I'm trying to tell you is that if you put a single Wilson line in compact space, it leads to some horrible instability.
Just flux has nowhere to go if the line is.
I think that Kumron may be able to explain better what I'm trying to say.
Okay, I can extend this question maybe. You don't have charged particles. That's what.
That's I agree.
But you can have. But you are introducing charged probes.
Yes.
That's a Wilson line.
Yes.
So he's saying that in a compact space, how can you introduce a charged probe?
Oh, okay. So Wilson line does not exist. Is that what you're saying?
I'm just saying that
flux has nowhere to go. So, for example, on a circle, where does the flux go? There's no consist. If you're
the Wilson line operator exists, but once you put it, the Hilbert space is destroyed. There is no vacuum in this theory.
So he says, what do you mean by Hilbert space on a circle if you have a charged object in one point?
Oh, okay. So you can calculate matrix element where you have Wilson line, flux, and then opposite one, and then compute the expectation value.
Yes.
And then you can have two Wilson line, and then you can calculate the matrix element. Are you happy with this?
Yeah. He's happy.
Okay, so good. So the advantage of this picture is that we don't have to talk about it. But if we want to talk about it, so I'm glad that you're happy. Then we can talk about it in that language. I didn't talk about it in the language of Hilbert space, so there is no contradiction between us. But if we want to state it in Hilbert space, what I can do is I introduce three operators. Wilson line, flux, opposite Wilson line, and then flux, Wilson line, and opposite Wilson line. Take difference and compute the expectation value. That leads to the same contradiction. But since I'm talking about algebra of operators and not the Hilbert, how it acts on the Hilbert space, that discussion is not needed here.
I also want to say one more thing, that the best interpretation of phi.
Okay.
So I completely agree with you in this language.
Okay.
But I also wanted to say that the best interpretation of phi is that it's a generator of a one-form symmetry.
Yes, I agree.
Because there are no
that.
charged particles.
I agree with that.
So that property would arise in any theory with higher form symmetry.
Right. Okay. Good. So there are more non-trivial examples. That's what I hear. Okay. So anyway, so actually, it's going a little bit longer than I expected. But yeah. So how much time do I have? Okay. So this is this is actually, I just wanted to demonstrate that this leads to a problem with Noether theorem, because it is exactly in a situation with pure Maxwell theory that seemingly global symmetry has no Noether current, because you can try to construct Noether current by using Noether procedure, but this current is not gauge invariant, so this is not observable. Yes.
Sorry, wouldn't you have said that flux quantization violates that symmetry anyway? I mean, you would have. I would have said that shouldn't be a symmetry because.
You can also consider. So you can quantize it. Here it's pure Maxwell theory, so the flux is not quantized.
Oh, you okay? Really?
R-gauge symmetry.
Yeah, it's a gauge symmetry. So there is no charged particle. Since there is no charged particle, so the gauge group is R rather than U1.
I understand. Thank you.
Okay, so you can also consider the case when the symmetry, the flux is quantized, in which case you can talk about discrete symmetry. But here I'm considering continuous symmetry because I want to demonstrate that there are no net current associated to it. And indeed, there is no net current. And you can actually be more careful and show that there is no way to improve this to make it gauge invariant. So this is actually consequence, in some sense, consequence of the non-splittability in this case. And indeed, so this is actually what Buchholz, Duprisha, and Lungo showed in their 1989 paper. That is that in a situation like this, then you can have a generalization of Noether theorem. So let me actually state it. So since I'm quoting them, so I can state it as a theorem. So this is Buchholz, Duprisha, and Lungo in '89. That suppose you have quantum field theory. Suppose you have a quantum field theory with split property. Suppose you have quantum field theory with split property, and then suppose you have a global symmetry G on the on this CFT. Respecting local structure of quantum field theory in the following sense, that first of all, G maps local operator to local operator, and at the same point. So it does not include space-time symmetry. And then second of all, the representation on the space of local operator is faithful. Well, if it's not faithful, you can actually consider a group which is smaller than G, and then consider that as an action. And then third, since we want this to be local, not contain space-time symmetry, so it's commute with energy momentum tensor. Okay, so then what these people showed was that for any subregion of the Cauchy surface, there is an operator which does the same thing for local operator on this. So this satisfies 1, 2, 3 on R. So this represents the symmetry G, but in this subregion. Okay, so this looks like obvious thing, but this is actually something that you can prove using this split property. And the great thing about this is that this applies to discrete symmetry. This applies to cases actually with anomaly, etc. So this is actually applicable to wider class of theories. Do you have a comment?
I like the way you say it.
Is it bothering you or?
No, I liked it.
We have division of labor. Okay, so I have a few comments to make. One is that, as I said earlier, I'm not aware of any quantum field theory. We should discuss about some topological situations where we have theory defined on Minkowski space without split property. So, for example, if you consider Chern-Simons theory, as Qumran pointed out, in flat Minkowski space, it's trivial. The Hilbert space is trivial. So there is actually nothing to talk about. And in the case of non-trivial topology like torus, then Chern-Simons theory has non-trivial Hilbert space. But it is exactly in that case that split property is questionable. So actually it does not contradict with the kind of question that you raised. And generically, we believe that even if the theory is turned out to be not splittable, you can always add some degrees of freedom in the ultraviolet to make it splittable. And
would that apply to Chern-Simons?
So as I said, Chern-Simons theory has RD is trivial, so there is nothing to discuss about.
So split probability applies to Minkowski space.
Right. Yeah.
He's talking only in the Minkowski.
Right. So in Minkowski space, I believe that all the quantum field theory I know of applies, and then therefore this is a true statement, given that assumption. Okay. So in the remaining maybe 10 minutes or so, I'd like to tell you why this is relevant to the question of absence of global symmetry. So yes, thank you very much. So I have 15 minutes. So thank you for the 5 additional minutes. So this is relevant for the question of holographic construction and the symmetry of such theory because of the entanglement reconstruction. So this is a feature of ADS-CFT correspondence that have been clarified greatly in the last few years, starting with Ryu-Takayanagi formula in 11 or so years ago, and that has been used more recently to understand duality holographic construction in more detail. So suppose, as usual, I draw ADS-C correspondence in this given Cauchy slice, and so this is a hyperbolic disk. And then suppose I choose region R in the boundary conformal field theory, then there is a Ryu-Takayanagi surface associated to it, which I denote by gamma of R. And so then there is a region which I'm going to denote as H of R, which contains between gamma of R and R. And actually, existence of such region is a part of the assumption of Ryu-Takayanagi formula, so-called homology constraint. Ryu-Takayanagi formula assumes that the Ryu-Takayanagi surface is homologous to the region on the boundary. So that means that there is actually a subspace on the Cauchy surface whose boundary is the same as the Ryu-Takayanagi surface and the boundary region. Okay? And then given this region, there is a region called the entanglement wedge. So I add the time direction to it. And suppose I choose this region. So here, this section is a section of this ADS space-time. And then there is a Ryu-Takayanagi surface. So this is R, and this is gamma of R. And then entanglement H is a domain of dependence of H of R, bounded by Ryu-Takayanagi surface and R. So pictorially, you can draw this type of region. So this kind of wedge region. So that's why it's called entanglement wedge, which actually is bigger than the generically bigger than the causal wedge of R. Yes.
Sorry, I just want to clarify. Why are we talking?
Is it on?
Hello? Yeah. I just want to clarify, why are we talking about homology? And previously you emphasized that we're talking just about Minkowski space. So where Minkowski space is going to be?
So homology, so for example, there is a question of what happens if you have black hole in it. That's what homology constraint means. So when you have a horizon over here, whether it wraps horizon or not. So on the boundary can have trivial topology, but bulk can have non-trivial topology. That's what a homology constraint means. It's a homology in the bulk, not on the boundary.
And connection to the previous discussion where we have strictly Minkowski space.
So it's in conformal field theory case, you can actually conformally compactify Minkowski space to sphere times the time direction. That's what I'm using here. Okay. So entanglement reconstruction is an observation that this boundary region R contains complete local information on low energy excitation in this entanglement wedge. So W of R is what is called entanglement wedge. So, entanglement reconstruction is a statement that any, so I assume that, as I said at the beginning, that bulk gravitational theory is describable in low energy in terms of Einstein gravity coupled to finite number of matter field. And within that low energy effective theory Hilbert space, you have a space of local excitation, and then any local information in that about local excitation can be included in the space of operator on the boundary region. And moreover, no information can be deduced from the region R about information about complement of this region. So you can consider complement of the entanglement wedge of complement. Sorry, so I have to be careful. It's an entanglement wedge of the complement, which is like this region. So entanglement wedge reconstruction is a statement that it contains this Hilbert the subspace. So this region R contains all the information in this local excitation in this wedge, but nothing in this wedge. So that's a statement. So so now let me discuss how this is related to what I want to show. Yes. Can you use microphone?
Just to clarify.
Can you turn it on?
Yeah. Before you raise this theorem, does it apply to conformal compactification you mentioned?
Yeah, so it's about 1 point conformal for the Cauchy surface.
Well, which changes topology drastically.
Yeah, but the split property is not modified by adding points. So. Okay, so now how this is related? So suppose you have a symmetry G acting on a global symmetry acting in this setup. Okay, so as I said, if G were continuous symmetry with natar charge, then it automatically means that there is a natar current and then there is a gauge symmetry in the back. So we don't have that, but we have we assume that the boundary CFT has split property. So what it means is that if you have since boundaries have the G is a symmetry on the boundary, so that means that for each element, small g of this group G, there is an operator acting non-trivially on the Hilbert space, which implements this symmetry. So it commutes with Hamiltonian and energy momentum tensor, and it transforms local operator into local operator in boundary. So split property means that if you split the boundary into segment, call that R1, R2, R3, R4, etc., then suppose this CFT satisfies split property, then the theorem by Buchholz, Duplicia, and Lungo says that there is actually an operator G of Ri associated to each one of this subregion, and then the operator that you want to construct is actually expressible as a product of this, because this does exactly implement transformation that this had. Okay? But this leads to contradiction, because suppose, so in the bulk, we also assume that we have global symmetry. So that means that there has to be local operator in the bulk, which implement this symmetry phase-free. So that means that there must be local excitation anywhere in the bulk, which commute non-trivially with this operator. But entanglement and reconstruction claims that this region knows only about entanglement wedge here, entanglement wedge here, 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 here. So that means that in particular, the local operators that any local operator you can construct out of here commute with this one. So this one too. So this means that on one hand, since this implement this symmetry, so this should have non-trivial commutation relation. On the other hand, this presentation shows that it commutes with this. Now you can ask, well, in a gravitational theory, can you define local operator? So in a low energy effective theory, there is a way to define it by using gravitational dressing. And then you have to construct an argument that says that the gravitational dressing commute with charges. But that can be shown because I assume that there is we are considering symmetry, which is not space-time symmetry, so that is an important part. So therefore, it requires that for given proper given transformation under space-time symmetry, there has to be at least two. So there has to be at least two operators with the same space-time transformation property, which transforms non-trivially under this group. So that means that these two operators have the same gravitational dressing because it transforms same way under space-time symmetry, but they transform non-trivially. So then using that, you can construct a composite operator, which for which the gravitational dressing can be cancelled, but still transform non-trivially under global symmetry. So even though you require gravitational dressing, you can state in appropriate way that gravitational dressing is neutral under this symmetry. So therefore, this leads to contradiction. So this is sort of essential part of the step 3 and 4. And so this is what I wanted to talk today. Thank you.
Any questions?
So how do we see from this argument that the violation must be by an operator in the effective action?
Yeah, so that's a very, very good question. And so as I said at the very beginning, this theorem as it is does not tell you how symmetry should be broken when you go to higher energy. So in the case of standard model, which is to be included in, you assume that it is to be included in GATT, then you would expect there will be dimension 5 or 6 operator that should violate baryon numbers. You would like to refine this theorem to say that there are always operators that to be added to low energy theory that is suppressed by the cutoff. And at least you may want to say that there is some power suppressed operator. But we have not been able to construct a rigorous argument for it. If you have an idea on that.
Baryon number is violated by the Hooft operator. You don't need GATT. You meant probably by B minus L.
Oh, okay. Right. Yeah, B minus L. Yes, excuse me. B minus L is still exact symmetry, which is violated by GATT. Yeah. Yes, some of other global symmetry can be violated earlier.
Yeah, by the Hooft operator.
Any other questions?
If I think about lattice regularization, suppose I think there is no continuous space-time, I have quantum field theories, and people are doing all this lattice simulation and so on. They have the scales that say lattice sizings that they put there, and the continuous theory when we send it to the zero. So if I think about quantum field theory only defined through the lattice regularization, does that tell me something about whether...
So this is related to our expectation that any quantum field theory can be made to split if you add UV degrees of freedom. And the lattice is sort of precise demonstration of this for some class of theories. Yes.
I would say almost all class of theories, which makes sense.
Well, you can. Well, so now the question goes to Simeon. So you made a claim in record that any quantum field theory should have lattice regularization, and Simeon probably has a comment on that question.
No. If.
You said no. You said no. Okay.
If it has a lattice regularization.
So if there is a lattice regularization, yes. So this is sort of back in my mind when I said that we expect that even if the theory is not splittable, it can be made so by adding UV degrees of freedom. And the lattice regularization is an example of this.
People would say that if it's not possible, so many lattice people would say that if it's not possible to give lattice regularization, then we don't consider such theories.
But we know example of chiral fermions.
We know, but they find some way out of it. But so, am I right that if the theory has lattice regularization?
Yeah. So as I said, I totally agree with the statement, and it was included in my expectations that I expressed during my talk.
Okay. Any other questions? So coming back maybe to Zohar's question, which you said basically there's a way to the Wilson line issue that you can put anti-Wilson line to get rid of it. So the big difference between...
If we want to state it in the language of Hilbert space, yes.
So it seems like a natural way to distinguish between global and gauge symmetries. And a global charge can exist in a compact space, but gauge charge cannot.
Yes, that's another way.
Could that be used as another way to try to argue against having global symmetries in the gravity? Do you see any connection with that?
Okay, so here I was... so in order to... So the statement I wanted to prove is that even if low energy theory has seemingly global symmetry, that cannot be made into exact global symmetry of quantum gravity theory. And so far we have been successful in understanding what quantum gravity means when you have interesting boundary on which we have holographic description. So in the case without in the compact space, that part is missing. So that make it difficult to discuss that. Some other aspect of my discussion, like split property, etc., can be enlightened by considering compact cases. I agree.
Any other questions?
So you talked about how the split property fails when you have a region which has non-trivial topology. And the theories you're looking at are gauge theories. And in particular, there was also this question about Chern-Simons theory. So in gauge theories, it seems like you might want to consider, instead of just the algebra of local observables, the full BV algebra, including operators of non-trivial ghost number. And I'm wondering if you consider that algebra, whether the split property holds for any topology.
Well, I thought that the flux operator and Wilson line operator still exist, even if you do the include ghost sector. So I don't think there is any modification to what I said.
In my opinion, split property is the same as saying no one-form symmetry.
So Zohar made a claim that split property is equivalent, that there is no one-form symmetry.
It takes in two dimensions, it's obvious, because if you have a local operator that is in the center, that's the definition of the one-form symmetry.
Okay.
Two dimensions is just the same as the usual definition.
Okay, thank you.
Any other questions? Okay, if not, let's thank Hiroshi again for a nice talk.